Hi, my name is Bill Fortney, and thank you for continuing on with me to learn about real-world data collection, to be able to gain information, to answer engineering questions, to have solid facts. You should have just finished the section talking about why measurement is hard, and this number two right here, understanding that the world is not a nice place, that the thing that you're measuring might be changing, which means we can't answer that question, what can I expect, because the thing is changing. And before we go in and look at the last, your measurements are only estimates, we wanted to camp a little bit on this one to see how do we tell whether our data is good or not, whether the population is changing. And so you saw before that there's two reasons why the measurements are different. And we mean measure the process and the measurement. Common cause, it's just varying because of randomness. What we see in the graph looks like data coming from one population, one distribution, they're just randomly changing. Or something happened, there was a special cause. Any of those variables that we've learned about, your background variables, your independent variables, the thing you're specifically changing, any of those specifically changed and impacted our data. It's not, the pattern is not consistent with one population. And what we saw is if it's consistent, stable, coming from one population, then we can calculate the average and standard deviation and use it to know what to expect. If it's not, then we need to understand the issue and resolve it. If the issue is our independent variable was changing, well, that's fine. We wanted it to change. We will then look at it as two separate populations, okay? But that's the idea that we've seen. And we saw that our population can be changing in a lot of ways. The average can be changing. The standard deviation can be changing. They both can be changing. They can be changing in a cycle. They can be changing up and down with no pattern. They can be changing like the case we saw where with one vendor's material, it's one way, with another, it's a different way. And so we saw that that's why that manager's first question was, is the process stable, so important? Because if it's not, then we don't know what to expect. Now, I want to say real quick, this idea of is the process stable is really a complicated question. There's a whole career, a part of quality engineering that focuses on process stability. It's a very important common thing in companies. They study their process. They look at it over time. They look at it under lots of conditions to understand, is it stable? And if it's not, to get it stable. That is the key way to make good parts is you look at your process, you make sure it's stable, you look how much variation there is in it, and you make sure that that variation is way smaller than the tolerance on the parts that you're making. So it's stable, it's consistent, it's within this much variation. So that way you're very confident that you're going to get good parts. Now, in your career right now, you're not worried about is the entire process stable over time. You're really worried about the second question that you were asked is, does the sample appropriate represent the real thing? And there's two pieces to that question. The first question is the process stable? And that's what quality engineers are focusing on. They're worrying about, okay, are we sampling such that my sample catches whatever's happening with the population? So in this case, yes. Down on this one, no, it doesn't. But good quality engineers would be sampling all different ways based upon what they know about the population, and they would get that. That's not as much your concern, except for when you're changing independent variables, you're going to sample under all those conditions. You're really worried about this second one, and that is, was the process stable while I was sampling? What you don't want to have happen is you're sampling. You're trying to ask the question, what can I expect out of you? And in the middle of your sample, the thing changes. Because then, if you try to draw conclusions, those conclusions aren't going to be correct. What can I expect? Again, now we're back to, well, when? Because the thing was changing over time. And we saw this here. Like when we had two different kinds of materials. If you took your sample here and you didn't know that was happening, well, then you would say your factory is producing here. That's not what's happening. So that's what we're really concerned with, is making sure that our sample, things aren't changing during our sample. And we're going to do this two ways. One, we're going to carefully design our experiment. We're going to do our homework. We're going to know what is known about the process. Like, especially if we're working in a company, we might talk to the quality engineers and they say, yes, we've studied this, the process is stable. We're going to know what variables impact what I'm measuring. And then we're going to design a sampling plan accordingly. We'll come back to this and you'll learn how to do that. The other thing that we're going to do, before we do anything else, we're going to look at the data to make sure that there are no signs in the data that it was unstable while we were sampling. Thus, we should not use it to draw conclusions. That's what we're going to be doing. And that is so critical, because if you remember, we've seen something similar to this before. Let's just say here's 3 samples from our population. And hopefully you can look and see that, okay, when I look at this one, this looks like one population, random. They're just jumping up and down, common cause variability. We're on the upper part of that graph, that diagram that showed either stable or not stable. So I can look at average and standard deviation, and I can use those with statistics to tell me what I can expect. Also, hopefully you can see that both of these, they're systemic. This is not random. This is not one population. Something changed. Something changed the average. Something changed the standard deviation. So what can I expect from you if this was my sample? Again, I hope you're beginning to see it's not even appropriate to calculate an average or standard deviation. What does that even mean? How do I ask, what can I expect about my population? Because it's changing. The question is, what is happening and why? Let me understand that. But what I want you to see with this is the only way you would ever know that is to look at it. Because all of these 3 graphs have roughly the same average and the same standard deviation. You would never know it unless you looked at it. So, big red stop sign, never ever use an average to describe data you haven't seen. Or take information from someone else that hasn't looked at a graph, at the data, to see if the average that you're giving you is valid. Because when you average, when you take numbers and average them together, you're saying that that average represents the data. But as we've seen, this top one, yes, an average would represent the data, would represent the population. Down here, no. If you created an average and said that represents what's happening with whatever that is data you took, that average is not describing what's happening, because what's happening is changing. You don't know when it's going to change again. So don't combine data into an average until you're sure it does in fact represent it. If the data has consistency, then you have reasonable assurance it's stable, it represents the true thing you're trying to measure, so it's okay to average, and then we will use that to predict what we can expect using statistics. So looking at it before you do anything to ensure you have a reasonable expectation that it was stable while you were taking information is critical. And that's why in our process, when we go to do an experiment, and you'll learn these details, the first thing we're going to do is design our experiment. You'll learn how to do that. We'll take all the data. We'll come and explore to learn all the engineering things we want to, but in between there, you're going to see this step, ensure the data set is valid. We're going to design it, take all our data, ensure that it's valid, that the process was stable while we were taking the data. Then we'll go and explore conclusions. So how are we going to do that? Well, to ensure that it's valid, we're first going to plot the data in the order that it was taken. We're then going to sort it by any independent variables and run order and plot that as well. We're checking everything that we measured, even if it's just a temperature, even if it's just some measurements, we're going to check everything that we measured, because any of those the process could be unstable. Even a typo is an instability in the process. And if you will do this check, you'll find typos, you'll find errors like that. But we're going to check everything that we've measured to ensure that the data is stable. There's not something weird with it. That's the population and the measurement we're looking at. And we're going to ask ourselves, am I seeing what I would expect to see if it was a stable random distribution with only common cause variation? That's what we're going to do. How will we know? Well, we've already seen it. We know what to expect from the normal. We turn it on its side. We realize, okay, we should see points distributed, bouncing back and forth. This graph right here, I just wanted to show you these 4 graphs. They are all normal data with an average of 81 and a standard deviation of 1. And I just want you to see we're not being picky like, oh no, look, these are bouncing up and down. There's a pattern. Oh, look, here's 3 in a row. No, we're looking for obvious things that says non-random. Random data bounces around and it has patterns. It has bounces around. We're looking for very obvious things. All of these are stable. Okay, so let me give you a couple examples. So we were going to measure wind velocity with the pedostatic tube in the wind tunnel at various RPMs to create the relationship between RPM and wind speed. We designed our experiment. Our dependent variable is the delta pressure, which we can convert over to wind speed. Our independent variables were RPMs, and we were going to have these levels right here of RPMs. And our background variables, there's a lot of them. Temperature, barometric pressure, how we read the manometer, whether we go up or down to reach the RPM. And we decided we were going to hold all of these constant. And temperature and barometric pressure, we're going to record. That way, if we see anything weird, we can go and look at those. Okay, so we want to we're going to do 4 measurements at each RPM. We took those 4 measurements, we gave them a random number, and we sorted by that number to randomize the order. You're going to learn that that's really important to spread anything we can't take into account across all the different levels. And first step now is we're going to plot it in run order. So we go through, we've got 4 at each one, and there's the data in run order. And we're asking, do I see anything that looks non-random? And I don't. That looks to me like it's just one population. I'm like, well, what else would I see? Well, let's say, for instance, barometric pressure was changing. A storm was coming in. So it was changing during the whole time that we were taking data. Then it's very possible that there would be an upward trend in all of this data that we would see. The data would be talking to us saying, hey, something was happening causing this to go up the entire time other than the things that you were changing, okay? That's what you're looking for. We don't see anything, so now we plot it by all the independent variables. And here we go again. And now here's the deal. We're looking to make sure that only random variation is happening, or variation that we put there. We know there's a difference between here and here. That is not random, that's systemic. Yeah, we know, we changed the RPM. So what we're going to do is we're just looking inside of each one of those groups to say, was randomness happening at each level there? We're making sure that there were no outside factors giving us a false reading at that RPM, at the next RPM. So we go through and look at each one of those. And yes, the process seems stable. Only common cause variation. I don't see anything there that tells me there was something non-random happening. Okay, how about this? What if we saw this? And obviously, that right there probably stuck out to you. That does not fit the pattern. Now, if all of these were bouncing up and down some, just there was a lot of variability at each RPM, then that would fit. But we're very stable at each RPM. Now, these look really like they're exactly the same. They're not. If we zoomed in on each one, we would see that they're bouncing up and down some. But at this scale, they're all pretty consistent. So to have one like that, that doesn't fit the pattern. Something odd is happening there. So in statistical terms, that would be called an outlier. It's not what we would expect of only common cause variation. There's a sign of a special cause. Something happened. So what do? In classical statistics, you throw out outliers, you assume it was a mistake. I don't take that approach as an engineer. And it really depends upon how good of a number you need. Because I know the world's not a nice place. What if the wind tunnel had some kind of glitch that every now and then the motor controller went down like that? Well, I would need to know that. That's pretty important for me to learn about my process. If I just throw out that data, I've lost that chance to learn. So the first thing that you would want to do is go and look at your notebook. Look at where you took notes during your experiment. Hint, hint, it's very important to take good notes. Did something happen? Did somebody come and talk to me? Did they interrupt me? Did something happen during that time? Because honestly, it almost looks like I forgot to change the RPM, and it goes with this one right here. I'm not sure, but that seems logical. But do I have a reason to believe that happened? Yeah, someone came and talked to me. So you know what? It's very easy to think that I just forgot to change the RPM and went on. You could do more testing to understand this. If you can't explain it, you either throw it out or you leave it in. And it's a personal decision. And part of it depends upon how much does it really change? Does that one point change what's happening a lot? How sure are you that it really belongs to this? How important is the decision that you're making? If it's super important to know, that's where I would go back and do some more testing to see, does this ever happen again, or was that truly a mistake? Okay, do you get the idea though? But that's why you plot it in this order, because things like this stand out like a sore thumb. And as a student, you will be surprised how often you find this, because how easy it is to just make a dumb mistake, to type a number in wrong, to switch two numbers, just to do things that stick out like this in your data, where if you hadn't have looked at them, you'd never see it and your calculations would be wrong. So do I move on to engineering analysis? Have you seen? You got to weigh the decision at hand, and you have to make the decision. And that's the way engineering is. All the math and everything, it gives you information, but you're the one that has to make the decision, put your name on the line, and decide what you're going to do. Okay, here's another example. We've got the flow rig. We have this orifice plate, which there's a pressure drop, and it's a way to measure flow by the pressure drop. You'll learn in fluids how to do that. And we've got two pressure transducers, and we're wanting to look at the relationship between delta pressure and flow. And we've got another flow meter to use as a standard. So the same kind of thing, we're trying to create that relationship. So our dependent variable is delta pressure. Our independent variable is flow rate. We have different flow rates. And background variables, water temperature is the biggest one, and so we're recording that. Okay, so we're going to plot it in run order and then sort it. And here's run order. And we look at that, and the first thing you may want to be is like, whoa, that's not random. Look at this. We got these points here. Well, yes, it is. Because notice we have 3 flows of 9 right here. That's why they're up there. Again, this graph isn't a lot of help unless there's something major going on. Same thing. It's very possible that if the temperature was drastically changing, we would see a slope going all the way up in this graph, or something was happening. We don't see anything. We're going to move on. We're going to sort it by the independent variables and looking to see, is there any outside factors? And hopefully you can immediately see that's not random. Every point at every flow rate is higher than the one before. Remember, these are plotted in run order. There's something happening at each flow rate. Again, likely it's temperature. The good news is I recorded temperature, so I can go and look. Remember, we're changing the channel on the data. So I would go do some different graphs and explore temperature versus flow rate to see if I could explain that. It's possible that I can. Also, I know temperature changes density. The orifice plate density is one of the things in the calculation. So it's very possible that I could look at how temperature changes, modify my density based upon the temperature, and recalculate. And all of a sudden, I could get all those flat. You see, there's the detective. You're not just looking for an answer, you're trying to understand the process. But you see, by plotting it like this right off, whammo, there it is, it's obvious. We see what's happening. Okay. So that should bring this section together. Hopefully you're getting the idea that anytime you have multiple measurements, they could be different for two reasons: common cause or special cause. If it's common, they're consistent. We can use statistics to tell us what to expect. If it's special, we can't. We have to understand what's happening first. And so this number 2 right here, the world is not a nice place. When we sample, we want to make sure that our data that we're using is consistent to draw conclusions. So we're going to carefully design our experiment. We're going to make sure the data is valid, be curious. And the first step is right here. We're going to make sure it's valid by plotting it in run order. Everything that we've measured to ensure our data is consistent. We're going to look for anything non-random. Okay, so then the last piece that we've got in terms of just a foundation for understand why measurement is so hard and what we're going to do it well to get good information to make our decisions is we're going to look at how measurements are only an estimate of the real value and what that means to us.